Welcome all. On the next part of topic gravitation, we'll discuss about gravitational potential due to solid sphere. So consider a situation that we are having a solid sphere and our aim is to find out what about the value of gravitational potential due to this solid sphere at a point which is at a distance x from its center. So let's say this is representing the center of sphere, and from the center of sphere we're just considering a point P which is at a distance, let's say x from the center, and our aim is to find out what about the value of gravitational potential over there. So we can find out in the same way as we discussed for hollow sphere. So just consider our first case. Take it as in case 1, we are considering if the value of x is greater than r. So if the value of x is greater than r, means the point is outside the solid sphere. So we can assume that total mass of the sphere m is concentrated at the center, and take it as its radius is equal to nothing but r. So if we are considering total mass is concentrated at the center, we can directly write the equation for gravitational potential, that is minus gm divided by distance, which is equal to x. Now if you want to find out the value of gravitational potential on the surface, let's say our case 2, that is when the value of x is equal to r, that means we are going to find out it on the surface. Then directly we can write the equation for potential, again considering that total mass is at the center, so it is going to be minus gm divided by r. Now if you want to find out what about the value of this gravitational potential inside a solid sphere, so we can just consider the situation something like this. We are having a solid sphere over here of radius, take it as r, and its mass is equal to m, and our aim is to find out what about the value of gravitational field inside a point. Just consider a point somewhere over here which is at a distance, let's say x from the center. So we can consider it something like this. It is the work done to take a unit mass from infinity to a point P. That will be the value of potential over here. So same as like in the way we discussed in case of a hollow sphere, we can just consider that first we are taking a unit mass from infinity to surface, then surface to a point inside. So we can divide this work done in two parts, that is work done by this gravitational field, or g of r dr, or g of x dx, and we are taking it from infinity to a distance or to the surface where the distance is equal to r. Then we can write it as minus of g of r dr, where the value of this is changing from surface to a point inside from r to x. So we can write as v is equal to minus of, and we know that the work done to take a particle from infinity to a surface is equal to potential on the surface, and the potential on the surface, we know the equation is gm divided by r. So instead of this term we can write it is equal to minus gm by r. We know that its answer is going to be minus gm by r. Now for the remaining portion, we can write this minus of integration of g of r. So over here this g of r is representing the value of gravitational field inside a solid sphere. So we need to write the equation for a gravitational field inside a solid sphere. That also we discussed, so you might be remembering that equation. The equation for that is gmx divided by r cube. If anyone is having any doubt about this, just go back to our previous lecture, which is related to gravitational field due to a solid sphere or inside a solid sphere. So there we derived this equation gmx divided by r cube. Into over here we are changing the x, so we can write instead of dr as something but dx, and we are changing the limit, or we are taking it from r to x. So we can put the limit from r to x. So we can write the value of potential is equal to minus of gm divided by r. Over here just remember an important thing, the value of this dx, basically we are taking that x, we are taking that particle from infinity to a point. So we are basically reducing the value of x, so the value of dx is negative, so we can put a negative sign over here. So just remember that. So this negative sign and this negative sign, it's going to be positive. So because we are not increasing the value of x, we are decreasing the value of x. So we can try this, it becomes plus integration of gm into x dx divided by r cube, and integration of this one from r to x. Now we can write as v is equal to minus of gm divided by r plus g is a constant, m is a constant, and r cube is a constant. Now we need to integrate this x dx. We know that integration of x dx is nothing but x square divided by 2, and the limit is changing from r to x. Now we can put the limit over here, so it is minus of gm divided by r plus, we can write this as gm divided by r cube, or if you want you can take this 2 also outside, and if you are putting the limit it is going to be x square minus r square. So we can write the value of this potential is equal to minus of gm divided by r plus gm into x square divided by 2r cube minus gm into r square divided by 2r cube. Now just to do for addition purpose, we can just take it as over here we are having the term of 2r cube, and here also 2r cube, and so here also we'd like to put that term 2r cube. So what we'll do is we can just multiply over here with 2 and divided by 2, and here we are having the term r cube, so we can multiply it with r square over here, and so it's going to be r cube, and here also we can multiply with the r square. So we multiply and divided by the 2 and r square. So we'll get the we can take this common term over here, so we can be written as, now this will be something like minus 2 gm r square, and here we are having minus gm r square. So if you are adding this equation and this term, so we are going to get as minus 3 gm square. So we can write this minus 3 gm r square, and the other term that we have is plus gm into x square divided by the common term or common denominator that we can take it as 2r cube. Or we can rearrange it this one as always we are writing this gravitational potential in terms of negative or something. So I'm just taking minus gm as a common, and this 2r cube also we can take it as common. So the remaining thing is nothing but 3r square minus x square. So it's a very important relation, and it is somewhat different relation as compared to the other relations that normally we are rooting minus gm by r. So need to remember this equation, that is minus gm divided by 2r cube into 3r square minus x square is the equation for a gravitational potential inside a solid sphere. Over here we can consider one more case, take it as case 4. That is if we are taking the gravitational potential inside this one. That means if the value of x is equal to 0. X is equal to 0 means we are basically measuring the distance from the center. So x is equal to 0 means we are considering a point at the center. So for a point x is equal to 0, let's say this is our case 4. So in this situation, our aim is to find out the value of gravitational potential. We can use this equation. This equation is for gravitational potential inside, which was minus gm divided by 2r cube into 3r square minus x square. Over here we can just take it as x is equal to 0. So the equation becomes g minus gm into 3r square divided by 2r cube. So we can observe that 1r square over here and 1r square over here get cancelled. So the final equation becomes minus of 3gm divided by 2r is a value of gravitational potential. So this is the minimum possible value of gravitational potential, because I'm saying it's minimum because it is the negative value. Then the potential will increase. On the surface we have a value of minus gm by r. Then again it will increase as we are moving away from the center, and it's going to be equal to 0 at infinity. That is a maximum possible value. So same as like a hollow sphere, in case of solid sphere also we can draw a graph which is showing the variation of this potential with respect to distance. So let's say this is the graph which is showing the variation of potential difference v with respect to distance x. And we know that when we are considering at the center, the value of potential is having least value, and the value of potential at the center is nothing but minus 3gm divided by 2r. And on the surface, this potential, when we are moving away from the surface, the value of potential is going to increase because the negative value is going to decrease, and on the surface its value is minus gm divided by r. So from here to here the potential is varying something like this. Potential is increasing means the negative value is going to decrease, and surface we know that its value is minus gm divided by r. Then again, if you are moving away from the center, the value of potential is decreasing, and at infinity it is going to be equal to 0. This is the graph for variation of potential with respect to distance. Hope so that you understood whatever the things we discussed in this class. If you are having any doubt, please contact. Thank you.